Okay, so today is the last bit. So there's a couple of things, or two or three things I think we've got to do. So first is approximating. The distribution of sample proportion. Alright, it's the second longest heading ever. So on the handout that I've given you, I've just used a random generator. So we're assuming 55% of the people in Australia have blue eyes, and then I've just created in this list what proportion of samples of 100 people, so 200 different samples. So here it's listed 1 to 18, it goes down to 200, and that's the proportion of people in that 100 people. So the first one there was 0.57 of those 100, so in other words 57 in that sample, and so on. So then when you graph that, excuse me, when we graph that, where on the horizontal axis we've got the proportion, so from 0 to 1, and on the vertical axis is how many samples fit into that. Alright, so where it's higher, in the middle, that's when more of these samples have that particular proportion. And so as you can see, and I've put a cross in the middle there, 50.55, which is what the population proportion was. And you can see from that it's, apart from a couple of little bits that are not exactly the same, but it's more or less symmetrical, and it's more or less looks a bit like a bell curve. And so then the bottom screen there shows of those 200 what the mean and standard deviation. So the mean is 0.55135 of these 200. So close to the population proportion. So what does that mean for us? It means that when we have a large sample and a large sample size, then it's approximately a normal distribution. So when we have a large sample size, the sample proportion that's P with the hat is approximately normally distributed. And if it's approximately normally distributed, then we use the following. So the mean is, we use equal to the population proportion, and our standard deviation that we use for the normal distribution would be population proportion 1 minus the population proportion over n, which is our sample size. Alright, so remember P is the population proportion, and N is our sample size. All right, I'm going to look at an example in the textbook. All right, so we're looking at the text, page 706. Example 11. Alright, reading it says, assume approximately 60% of people have a driver's licence. Using the normal approximation, find the approximate probability that a randomly selected sample of size 200 that more than 65% have a driver's licence. Okay, so population proportion, so that's the first bit where they say assume 60%. So our mean would be 60%, which of course is 0.6. Our sample size N, well, it says that, selected sample size of 200. So if we're going to use the normal distribution, we need the mean and we need the standard deviation. So standard deviation is the square root of P, which is 0.6, times 1 minus P, which is 0.4, over our sample size of 200. Now, because I've prepared this earlier, that becomes the square root of 0.0012, which becomes, to 4 decimal places, 0.0346. All right, what have we got to find? Blah, blah, blah. Find the approximate probability that in a random sample, blah, 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 more than 65% of people have a driver's licence. So we are after probability that more than 65%, so more than 65%, 0.65, have a driver's licence. All right, so what is it then that we're looking at? We're actually looking at the proportion in that sample. So we want the proportion in that sample of 200 to be more than 65. 0.65, not 65, 65%, 0.65. All right, so we have a mean, we have a standard deviation. What's the probability that this sample of 200 we're going to look at has a proportion of more than 0.65? We go to our calculator, interactive distribution, continuous, norm, and our lowest greater than 0.65, so our lower limit is 0.65, 0.65. Our upper limit, well, it's anything up above that, For this particular one, however, what will our upper limit be? 1. Because we're talking about a proportion, aren't we? So, a proportion of 1 is everybody, isn't it? Alright, then we've got a mean and a standard deviation. We need to change those. So remember the default is for the normal standard. So we're changing 0.0346. And our mean is 0.6. And away we go. There it is. So 0.742. So the probability is 0.0742. So in terms of percentage, the probability is about 7%. So there would be not too many samples of 200 that you would choose where you would get more than 65% of those people in there with a driver's licence. All right, anything about that before we move on to the next bit? All right.
Is that the end of that example?
That's the end of that section. So there's 2 other bits. Alright, so quite clearly the sample proportion will vary from sample to sample. Not very likely that you're going to get more than 65% in this, but however it is possible. So what we are asked to look at now is what we call confidence limits for the sample proportion. So confidence intervals, if you like. Yeah. Or sample proportion.
So did we just do 17C, now we're doing 17D?
Yep. All right, there's a couple of things. One's called a point estimate. And a point estimate is when you use your sample. So you take a sample, you find the sample proportion, and you use that to represent the population or to estimate the population. Alright, so I could do some sort of survey and I could survey a group of people and I could come up from that survey, the group of people that 65% of them do whatever it is, and I can say use that to estimate the whole population. Alright, so that's what the point estimate is. The next thing is that we can use is what we call an interval estimate. So rather than just using the 65% that I found when I did my sample, I can use that sample information and I can come up with a range that's going to fit in. Because you can see just that 1 point may or may not be close to the population, but if I can come up with an interval and say, well, for the population it's between here and here, it's probably going to be more accurate. So how do we do that? So that's when we use a confidence limit, or confidence interval. Now we've already done these. Alright, so 68, 95, 99.7 is what we're talking about here. And so we're using those to come up with a range that the population proportion would be in. So for our standard normal, I'll change that colour's running out. So for our standard normal, the 95% one is so our Z value, 95% of the time, our Z value lies between negative 1.96 and 1.96. So for a standard normal distribution, here's our standard normal, which our mean is equal to 0 and our is equal to 1. Then between there and there, in this bit here, that's where we have 95% is in there. So the mean minus 1 standard deviation, plus or minus 1 standard deviation. And there's a slot of 2 standard deviations, I should say. And you'll notice it's not exactly 2 and minus 2, it's a little bit different. Right. Which bit?
The blue part.
Oh, the blue part's still there. Alright. Alright, and that little bit of difference, again, remember that's because this 95% confidence is not precisely exactly, but close to. Alright, so what if we do have a different sample size and a different proportion? So it's all very well to have a mean of 0, standard deviation of 1. In reality, when we go out and do stuff, that's not what we end up with. We end up with a sample proportion and a certain size of sample, whether that be 50, 100, 200 or whatever. So for a sample of size n and sample proportion P hat, this translates to Alright, so our confidence limits, so the 1.96, see that's there, that's the 95% bit. Alright, so instead of the mean, which in this case was 0, we've now got a mean that we're approximating by the sample proportion. And then we've got to take the standard deviations away from that, and here's our standard deviation, how we work that out, and then to the mean plus. Alright, let's do an example.
So does 95% lie?
So there's 90%, we have 95% confidence that when I go out and I take my sample of however big, looking at how many are left-handers, for example, and I get my proportion from that sample, I have 95% confidence that the proportion that I've come up with will lie between these two values. Or that the actual population proportion will lie between these two values. Because this is what the proportion I got when I did it. So we're saying, how does that relate to the whole population? And you say, well, 95% confident that the population proportion will lie between those things. All right, let's have a look at an example. Again, I'm going to use textbook 1. All right, so text, page 709, example 12. All right, so in this question, the first bit says find an approximate 95% confidence interval. So this is the interval that we're looking for. So between this number and this number, we have 95% confidence it's going to be in there. So that's what we're looking for. All right, what else do we need? We need to know our number and we need to know our sample proportion. So what are we told? The proportion of primary school children in Australia who regularly use social media. All right. So Australia's the population, so it's the population one we're looking for, and it's going to be in between these numbers. 95% confident that it is. What have we got? We've got a sample of 20 children. And of those 20 children, we find that 0.7 of them are using social media regularly. All right. So for our 95% confidence, we're using this thing here. So 95% confident is our sample proportion, 0.7, minus 1.96 times 0.7 times 0.3 over 20, between there and 0.7 plus. So somewhere in that range, we have 95% confidence. All right. can do that in your calculator. And when you do that in your calculator, because I've prepared it earlier, we get these numbers. So what does these numbers mean? What they mean is that we can say with 95% confidence that across the whole of Australia, that the proportion of primary school children across the whole of Australia that use social media regularly is between that. So somewhere between 49.9% and 90% of primary school kids across Australia, 95% confident that it will be in there somewhere. Not a real good range. All right, 0.49 to 0.9, that's a big range. The issue with this number is, anyone guess?
Do you have to round it?
No, not rounding it. It has to do with one of these up here.
Oh yeah, it's greater than the sample proportion.
It's not so, not this, it's this only 20 people we've looked at. So we're trying to estimate the whole of Australia based on just 20 people.
Is that saying that like 20, so can you...
So the actual, if we went and did it, everyone in Australia, every primary school kid in Australia, and worked out what it actually was,
Yeah.
from our sample of 20, we're 95% confident what the actual value will be between those.
Out of 20.
So we only used 20 kids out of every primary school kid in Australia, and this is what we come up with. So the issue is we've only used 20 kids, so that's why we've got such a big range. So if we'd used more kids, we'd get a smaller range and we'd be closer to what the actual is. Any more questions about that? Because I know it's a little bit confusing as to what it means. All right, so thus the actual population all right. Okay. Now, the 95% is the one that's mentioned in, I think, the study design, but it doesn't have to be. So we can generalise it. To this. All right, so the bottom end is our sample proportion minus some number, Z. I'll get to what the Z is in a minute, times by the standard deviation of our sample. the bigger this number here will be, the smaller that standard deviation would be. And plus Z. In. So this Z comes from our standard normal. So, what are those Zs? Those Zs are this. So for 68% confidence, which is the mean plus or minus the standard deviation, the Z we use for that is 1.65. All right, before you start to panic about how you're going to remember this, and this sort of stuff you're going to have your calculator for. It's not the sort of stuff you're going to get on exam 1 where you haven't got your calculator. All right, so it should be in your bound reference. So 68%, 95% is the one we've just done. And that's 1.96. And the 99.7% one is the 3 standard deviations. And Z for that is 2.58. Alright, so we're going to do example 13, so not much information there. Alright, it says, a survey found that 237 out of 500 undergraduate university students. Alright, so, what have we got? The number of ones that we've got is 237 out of how many? Out of 500. So it's just representing the thing we're looking for, whatever it is. 237 of them out of the 500. It says find a 95% confidence interval for the proportion. Alright, so we want 95% confidence. Alright. So what we're going to do is use our calculator. So in our calculator, go to statistics. So I'm going to have to get out of my main screen and go to my menu and statistics. Then in our statistics, we want to calculate something. So we go to calc. So we want to calculate a 95% confidence interval. so here we go, calculate. And we got a whole bunch of stuff. Test interval distribution, inverse distribution, dip stat, whatever that is. What are we doing? 95% confidence interval. So we're looking at interval. All right, so then we've got this other thing. We want to go, so we got the right one there, this one here. One prop Z, that's what we're after.
Will we ever need to use something different?
No.
Cool.
I don't know what that one prop's supposed to mean, but what it is. So one prop Z, then we go next. Then we get this stuff. Sea level, what do you think sea level means? Not sure?
Confidence level.
Confidence level, go help. And it says confidence level. And the confidence level we're after is 95%. 0.95. X, the data. Alright, so what did we get? We got 237. And how many sample size? We did 500 people. Then we go next.
Oh my god.
And we get two numbers, a lower and an upper. So 95% confidence, our interval, 95% confidence that the population proportion would be between 0.302 and 0.5178. All right, a much smaller range than we had got in that previous example. Here we've got 500 people, not 20. All right, so the what I did in the previous example by hand, this is how you can get the calculator to do it for you. All right, last bit.
How do you get what? It pops up in the calculator.
All right, any questions about that before I move on? All right, the last thing is precision or margin for error. Of error. All right. The standard deviation. Of the sample. Is the square root of the sample proportion times 1 minus the sample proportion over our sample size. Now, what is standard deviation? What is it? What does it tell us? Spread, exactly. So, spread, we can say then if it's spread more, if it's spread less, that has to do with the precision. Something that's spread less would be more precise than something that's spread more. All right. So if I'm trying to throw a bit of paper in the bin there, I've get lots of bits of paper around the bin. I'm quite precise with my throwing, but if I've got bits of paper from here all the way around to there, I'm not very precise with my throwing. Alright, so standard deviation, so this indicates the spread. And hence precision. Now, already mentioned this before and mentioned about it in the two examples. If we want to increase our precision, we've got to do something about making this smaller. So, increase our precision or decrease the margin for error. Then we've got to make this smaller. And the way we do that is to enlarge that, make that bigger, and that's going to make it more precise. So we increase the sample size. Alright, so remember the sample proportions, they're numbers between 0 and 1. So we're not going to be able to change that very significantly. But our number is quite easy to increase our sample size and make a difference that way. Alright. So our margin of error then, so I need to define what margin of error is. And then do an example. Defined as the distance between the sample estimate and the endpoints of the confidence. All right, so for the 95% confidence interval, it's this. Alright, use M for margin of error. It's this number again, the 1.96 square root sample proportion, 1 minus the sample proportion over sample size. So that's the margin of error. So remember in our confidence intervals, one of them was p hat minus that, and the other end was p hat plus that. And that bit of it is the margin of error. So we think it's this, we go that much either side, and this is our margin of error. Alright. Of course, if you wanted the 68 or the 99.7, that number there would change accordingly. Alright, last example, and we're done. No one out of the text. Seven 12. 15. Right. Determine the sample size required. To achieve a margin of error of 2%. So margin of error 2%, as a decimal that's 0.02. In an approximate 95% confidence interval, so 95% confidence interval of our primary school children in Australia use social media, and the sample proportion, P hat, has been found to be 0.7. So what we want is, in that previous example I showed you earlier where we only had a sample size of 20, we had a big range in that, didn't we? From what, about 49% to 90 or something like that, something around about that. So it was a big range, so big margin of error. So we want that margin of error to be much smaller. So how many kids? A lot more than 20 you would think, but how many do we need to do so that we get that a lot smaller? Well, this is what we use. So our margin of error, we want to be 0.02. 1.96 square root of, where are we? Sample proportion, 0.7 times 0.3 over n. Because we're going to have our calculators, we would use solve in our calculator. And when you do get your calculator to do that, because I've prepared it earlier, you get that you need 2016.84 students. Not sure we get someone to volunteer to be the 0.84 of a student. So we need a sample size of
2017.
2017. There we are. Done. All right, that's it.